Yeah, Rajiv, you're good.
Oh, no, great. Thank you so much for having me. So what I want to do today is, if you're unfamiliar or new to data science, what I want to do is be able to go through how you should be able to ask any particular machine learning model you see and be able to explain it and understand several facets about it. And for those of you that kind of are more comfortable with interpretability techniques, hopefully we can press and go a little bit deeper on those. As we go through this, if there's questions that come up, I do have the chat window up on another monitor, so I'll kind of keep an eye on that. And if there's, I'll pause at times for questions, and if there's kind of questions that are relevant, I'll try to work those in as well. All right, but let's get started. As you can see, kind of I have the dragon theme. It's a little dated, but it still makes it a little bit more fun than kind of, all right. So, you know, one of the things we want to do is imagine this scenario of dragons. What we want to do is we want to use machine learning to help us figure out which dragons are likely to eat us, right? This is obviously something that we care a lot about. None of us want to get eaten. So having a machine learning model that helps us do that. Now, if I did this talk probably 2 or 3 years ago, I would have probably focused on, let's say, a deep learning predictive model, right? I mean, the hype cycle is a little over for that now, but one of the things you'll hear about a lot is interpretability now. Now, we're going to focus today on interpretability, but one of the things I like to mention is that interpretability is a small piece of a larger picture around trust. And this is where there's lots of questions that come up. For example, is your data biased? Is your model being used for an ethical purpose? So think about all of the debates we're having about with facial recognition. Is your model continuing to be trusted over time? Have you put into place model monitoring and management? So there's a whole vast set of questions around kind of the trust, bias, ethical issues with machine learning. I'm not going to focus on that. I'm going to focus on just a small piece here, which is, if we have a machine learning model, can we explain what's going on? Can we help understand what's going on? And so we're going to focus today on building this interpretable model around aggression. Now, some people might be like, well, why bother with interpretability, right? Why not just stick all my data in the TensorFlow, look at my metrics, and if the metrics are good, go ahead and deploy it? Well, I think there's a couple of audiences why we care about interpretability. So the first one we care about is yourself. So it's very easy for things to go wrong in machine learning models. It's also important to debug your models. So interpretability comes into play to help you understand what's going on in the model to make the model better. The next piece is, well, now that your model's good, right, you're comfortable with it, as soon as you go to your manager, your boss, somebody else, some other stakeholder, they're going to be like, well, okay, I see you got this machine learning model and I see this fancy AUC, but like, tell me how it works, right? What's going on inside it? And so interpretability and explainability come and become factors there. And then finally, for some segments, so you can think about like insurance, financial services, healthcare, there's a higher standard set. There's regulators, there's government regulations that ensure that, hey, if you're going to take this model, because we know that there's a lot of risk that it might have to our financial system or to the health and welfare of people, we really want to understand what's going on with that model before you put that out. So these are some of the reasons we kind of care about thinking about interpretability with our models. So let's start with kind of the simplest, easiest, most interpretable model, right? So this is kind of in our traditional, kind of what I would call a very understandable white box model. So in this model, you'll see we have just 2 features or variables, the number of bathrooms and the square footage. And the idea here is to be able to predict what the value of this apartment is going to, or what the value of this house is going to be. So you can see we've got 2 bathrooms, right? You can, the coefficient for those of you, right, is kind of 350,000. We can multiply number of bathrooms and the square footage. So, I mean, what do folks think? This is where I miss having the live audience where I can talk to you, right? Is this a pretty understandable model? Is this kind of nice and easily explainable to you? So to keep me entertained, please type in yes or no into the chat, just to kind of, that way keep you guys a little bit warm, and that way I can see some stuff going through as well. All right, so Nick says yes, good. All right. Looks like there's not a lot of people questioning whether this is something that's, right, we can explain this model. So now let's get a little bit fancier, because, right, data scientists, we like to be a little bit more accurate, and maybe by adding some other features in, we can actually build a bit better of a prediction model. So let's take a look at this model. I've added in some more features, right? Hopefully with the idea, by adding in these features, I've built a more accurate model. And now you can see I've made this very transparent. I've shown you all the coefficients for everything. How are people feeling? Is this still a very understandable kind of model?
But like, I just want to ask, like, what about the correlation between the target variable and the rest of the variables? So we should even consider that as well, right? If there is some correlation, then we can think about the right model. We are just looking at the coefficients and the features that might help in predicting. But what if we, like, you know, because by using the correlation, we understand how each of these features are affecting the target variable.
Mm-hmm.
So by understanding that, we can then, you know, yeah, we will be able to understand which model or what type of model we should go for.
Yeah, and so you're getting to a little bit more advanced thing that I want to get to in a little bit, with the relationships between the different features. But if we were kind of using this, does everybody agree that this is a pretty understandable model, right? I've given you the coefficients. It's easy for you to understand exactly what the prediction is.
Yeah.
Right? Is there, right? There's nobody that finds an issue with the fact that, right, as my square footage goes up, I multiply it by 1,000, right? But as the total rooms gets higher, the value of my house goes down, right? Because we know, right, houses with lots of rooms have very low values, right? Does this make sense to people, or are people a little bit confused now?
So yeah, I think, actually, I'm a bit confused on this point. Well, after you clarified it.
And so this happens all the time, because this is something that you mentioned earlier, is that all of these features are not entirely independent from each other. There's relationships between the features. The machine learning models can deal with this to give you an accurate prediction, but if you try to interpret just the coefficients here, it can be very confusing. And I've seen this in many marketing. Marketing, for example, likes to still use coefficient-based models. They often will have features that are kind of related to each other. And so you'll have these kind of effects like this that you have to kind of try to explain to a room full of people, like, how come, well, all of a sudden, right, if we want houses that are worth a lot, we're not looking for houses with 2 rooms, right? Like, there is a relationship between rooms and the value, even though this model kind of doesn't pick it up. But this is where it gets tricky, when we start adding a lot of features in, and the features are correlated to each other for understanding a model. Now, this is typically when, this is, right, traditional statistics, right? We learn this, but newfangled data scientists will be like, oh, right, we don't do any of this kind of linear models. We use a higher order, right? We use things like decision trees. And decision trees are kind of very understandable. So unfortunately, I didn't write this up for the dragons, but you can kind of get the idea here. This is the classic Titanic problem. So we want to be able to, in this case, predict who's going to survive or not. How do people feel? Is this a pretty understandable model for what's going on? I mean, we only have 2 features, right? And we kind of clearly kind of say how we want that. So for example, right, if we're kind of, if you're a male and your age is greater than 10 years old, right, your chance of survival is very low compared to, for example, the non-males. So, I mean, you know, for me, this is fairly easy to explain. What's the downside of this easily explainable model? I mean, this is the classic CART decision tree. I mean, we could just kind of stick with this and just all go home and we'd be great. But yeah, accuracy, right? So I gave you one with 0.74, but again, the goal of our machine learning models is to try to do as best as we can to mirror what's in the real world. We're never going to be able to do that exactly, but often the more variables or features, the more data we use, the better we can get. So, and in this case, if we start with just those 2 features, we get an AUC of 0.74. And for, just to make sure everybody understands, the higher the AUC, the better. We'll just leave it at that. So what we can actually do is we can actually add more information to this. So by adding more features or variables and allowing the tree to become a little bit more complex, so you can see there's a lot more decisions going on within this tree, the performance of our model increases. And we don't have to kind of stop there. We can kind of keep improving it. So you can see now at this point, right, it gets a little tricky, right? There's a lot of features and it's a lot harder to understand what's going on. And if you think this is bad, right, what do data scientists like to do? They don't like to use kind of just one tree, right? What do we call a collection of trees? Right, it's the kindergarten question, right? The collection of trees, right? It's a forest, right? And the forest, we know kind of, right, from our machine learning, by that kind of wisdom of the crowd, by taking multiple trees together, we can actually kind of use that ensemble to build a more accurate model. But this is right when you really have to start scratching your head and start thinking like, how am I going to explain what's going on here, right? How am I going to understand what the most important feature here is, right? How are all these features being used? What are the variables? Hopefully at this point, you kind of get the idea of that. So yes, AUC is kind of you can think of it as a proxy for accuracy. Now, I just talked about 2 algorithms so far, linear models and decision trees, but really there's lots of other types of algorithms out there. So this is Randy Olson. He runs the Reddit visualization. He's a big kind of data science influencer. And he ran a study where what he did was he took a lot of 165 different data sets, ran them across a lot of different algorithms, just typical scikit. And one of the things you find is what's called the no free lunch theorem. There's not one approach that always works the best. And so when we start thinking about trying to explain or understand our models, we have to realize that in data science, you know, it's best practice to try lots of algorithms. We need some method that's going to go beyond that. And so this is where it gets tricky, right? Because we need to find a way to figure this out, because if we can't figure out if this model is going to work or not, we're in trouble. But all is not lost here. So what I want to kind of do is we'll go through here and explain how we can kind of start doing this. But I want to highlight, you know, my position is that, you know, most simple models are just not very accurate. If you can make a simple model accurate, that's great. Typically, most of the problems that data scientists and machine learning gets are complex problems. If they were simple problems that could be solved with a couple of rules, we would do that. So I have the slide deck here in a GitHub, and you can kind of, I'll share that with you at the end. So if you want to kind of dive into further resources, those are available, for example, on diving into kind of the issues I talked about with multicollinearity. Porsabi is the one where I use the example from the linear models that she has in her paper. other papers around simple models and defenses of black boxes. But I want to keep going here because I really want to focus on, there's tools here that can explain any black box model. And what I want to focus on are 3 tools and 3 ways that I want everybody to walk away with. One is understanding what are the most impactful features or variables in a model, something we call feature importance. 2, understanding the directionality of these features. And here we're going to talk about a technique called partial dependence. And then finally, at the end, we'll talk about the importance of explaining a prediction. And we'll kind of talk about the methodology of Shap values here. But these are 3 things that I think everybody should be able to do, or anytime you see a machine learning model, you should be able to understand what variables are most important in the model, how are they important, and for a particular prediction. So, and by a prediction, I mean how it's influencing some person or something. You should be able to understand what's driving that, what's going on with that. All right, so let's see. Keep asking the questions as we go on. I'm going to keep kind of pushing ahead with this. So the first thing I like to kind of highlight is feature importance. So if we come back to when we're building that model for dragons, one of the things we're going to go out and do is we're going to use a lot of features, a lot of variables. And typical kind of good practice of data science will be, let's go ask the domain experts, right? Let's go spend it, not an evening, but a couple of days watching all the Game of Thrones and understanding, right? What is it about a dragon that makes it likely to eat somebody? Start taking all those factors in and collecting that data to help us build that best machine learning model, right? Maybe it could be the age, the weight of the dragon, if it has kids. All of these things could come into play. Because really at the end of the day is we want to understand what are the most important features that are in our model. What is driving our model? This is important for explainability, for debugging it, for just figuring out feature selection, lots of pieces like that. And so it has real consequences of being able to get and figure out what are the variables that are driving a model. And so again, this is my fun ones here, right? Because if you don't figure it out, you're going to be toast. Oh, non-stationary. Okay, so for now, I'm going to avoid the time series pieces like that. So we'll talk a little bit about that in a bit. So let me start with kind of a simple example. And I'm sticking with the dragons, and imagine kind of a dragon. Imagine we want to understand kind of how dragons learn to read. So what we want to do is build something that affects reading for dragons. And I picked reading because it's something that all of us intuitively understand what's going on. So that way, when I show you the actual data, you can kind of see through it. So if we think about what affects reading, I think one thing is, we're looking at children here. Think about, from 3 years old to 18 years old. I think we're all probably agree that age affects reading, right? A 5-year-old is going to have a very much of a different ability to read versus a 13-year-old. So if we're building that machine learning model, it's going to be that. On the other hand, let's take another factor, milk. How does milk consumption affect your reading? Any guesses on this?
The lower the better.
So the lower the better. So the less milk you drink, the better reading you get.
Yeah.
Is that what you're saying?
Yeah.
Why is that?
Because when you're a baby, you're going to drink a lot more milk. As you grow up, you're going to consume a little less.
So my initial thinking, maybe not without thinking at all, I thought it would be the other way, right? That somehow like the more milk you drink, the better. But your relationship is right. I actually looked at the Milk Institute has studies on this. And it's basically, right, like teenagers don't drink milk, right? And they're the ones that kind of have the best readers versus, right, as you say, like the babies and the small children are forced to drink milk all the time like that. So we know milk consumption, right, is a feature that's probably, that's related to age, but really has nothing at all to do with the ability to read, right? Whether or not you kind of give a child 1 gallon or 1 pint of milk probably is not going to affect their ability to learn to read, their reading scores. And so this is kind of a data set from, it's the party package, I can't Strobel, who has a classic some papers on permutation importance. But this is what the data set looks like. And the idea here is we want to be able to predict the reading score. And if you just quickly take a look at this, you'll see that both kind of age and milk consumptions have a rough relationship here with the reading score. Now, right, but one of the values of machine learning models is they actually use the data to figure out kind of what are the actual features that influence it, the reading scores, versus things that just might be related to it. And if we actually run this through machine learning models, what we find here, so let me get here, is if I use, so this is light GBM, and if I use the default importance that comes out of a light GBM model, which is a split-based variable importance, that basically just counts the number of splits in the tree, what I find is that milk consumption is actually the most important feature in this model. And it's the most important because it just shows up, it's related to age. So the model itself, when it's making the splits to build predictions, has a lot of those milk consumption things. But if I use a different technique, and we'll talk a little bit about how this technique works in a minute here, is a permutation-based approach, it cuts right through that and recognizes that really it's age that has that relationship, while milk consumption doesn't really have a relationship between milk consumption and the ability to read. Now, this problem that I point out happens all the time when we're talking about working inside an enterprise, because a lot of times you'll be handed a data science project and you'll just go to some enterprise data lake and just grab a huge table of really wide data. You don't have the time to go through and kind of read all of that. So it's very often when people don't have this domain knowledge and understand those features, they can kind of fall for these types of relationships. But let's talk a little bit about permutation-based feature importance and how it works. All right, so let's just kind of start by building very simply 3 different models here for 3 different models. We have 2 features. We're going to build 3 different models. The first model here is going to have both features, and it has an R-squared of 0.9. Now, the higher the R-squared, the better the model is. And then I'm going to build a model A over here, that just uses the feature A. And you can see what its R-squared is. And then I'm going to build a model with just using variable feature B. And you can see the R-squared there is 0.8. Now tell me, which feature do you think is most important in that model AB? Is it feature A or feature B?
Feature B actually gives a slightly better R-square value as compared to feature A.
Yeah.
So that's why I guess feature B is better, predictor for the result.
Yeah, I mean, come on. You guys are probably like, this is silly, right? I told you that this has more signal in it with the higher R-squared. Like, of course, this feature is more important. But let me actually set up the problem a little bit differently and have you think about it in a different way. Instead, let's think about it starting from model AB. Now, for model AB, if I just remove feature B, how much does the performance of my model drop? Right? If I just remove feature B,
it will be 0.1. I mean,
right? If I
feature
just
B,
use
feature B, right? Oh, so it's 0.2. Yeah. Oh,
yeah. Yeah. Right. While if I kind of remove feature B and just have feature A, you can see when I remove feature B, my model performance drops by 0.2. So this is another way of getting to that same idea that feature B actually carries more importance in the model. Does that make sense? So let's do this again here. And so the technique I'm using is basically what I'd call an ablation methodology. It's leaving something out and seeing what the effect is. And one of the things I always like to do is I like to always kind of run the experiments on my kids. So like when I was working on image classification, I would take my little, at the time, kind of 2-year-old to the zoo and have him kind of ask him about strange new animals and say, no, is that more like a dog or a cat? And kind of see how he would classify things. Well, you can do the same thing with this ablation methodology. If you want to try to understand what's important to something, you can try something with it and without it. So one of the easy experiments to run, and I've kind of run this with my wife, for example, is what I can do is I can spend a day where I give her coffee and I don't give her coffee. And it's very easy for me to then understand that coffee, for example, is something that makes her happy. But we can explain and take these same concepts and apply this when we're thinking about looking at that feature importance. So let's look at a slightly more complicated example here. So now I have 3 variables, A, B, and C. Now, if we take a look at this, we can see what the performance is when we've left each of these features out. So now, based on this, which feature do you think here between variables A, B, and C is the most important?
C.
C, right? Because as soon as we remove C, the performance goes way down, right? So this is what we would call kind of a leave it out importance. And for those of you kind of thinking this through, you can see, oh boy, what happens if I had, 100 features or 150 features, right? I'm building out 4 different models in this case, right? That's going to scale up. That's a lot of machine learning models to build, right? I mean, Amazon would be quite happy if you're going to build all that stuff, but it's probably not in your best interest in your bottom dollar to kind of do that. So this is where kind of a long time ago, right? Bremen kind of came up with this idea, well, instead of actually building those different models, what you can do is actually just shuffle the feature. So we can, within the one column of the data, we can permute, change the order of the features. And by changing the order, you essentially, it's analogous to removing that feature from a model. But the nice thing is now we don't have to kind of build additional models. And so this is essentially the idea of the permutation-based feature importance. Widely used, right? If you kind of go, our package has the permutation-based importance. I think Python finally added sklearn, now supports permutation importance. And so it's essentially kind of a nice standard kind of best practice for thinking about feature importance of models. I'm gonna skip by some of these. Oh, go ahead.
Wouldn't you care about the correlation of the features as well?
So yes, so this is a bit more of a technical question, right? So feature importance, I was gonna try to skip this part, but I can hit it. So in the feature importance, we're looking at one feature by itself. But one of the things, right, we talked a little bit ago is that we know in reality, features are often related to each other. We get this kind of multicollinearity. And so one of the things that happens, if you, for example, run and build 10 different models on the same data, you can often end up with 10 different feature importances, a little bit because of maybe how the data is partitioned, as well as maybe how the random seed is set for how your algorithm is working. And partly what this happens is that this multicollinearity can really affect when you're interpreting model. And the idea here is that you have lots of features that are related to each other, but they're each sharing information about the target. And we can share them in different ways. So for example, you can see in this case, kind of how these features are kind of moving up and down in different model runs, because again, they're sharing related information. So this is where it becomes a bit more nuanced and complicated when you're trying to interpret things, when there's actually multiple pieces of information that are sharing the signal for that. And so this is where kind of people start wringing their hands, and right, I mean, one thing people like to do is, well, let's remove multicollinearity. Well, the problem with removing multicollinearity is often your model performance will drop quite a bit because there is a bit of information that this is doing. And then it becomes kind of what's important to you. So, and I really didn't mention this early on, but a lot of the stuff that I'm talking about matters if you focus on explainability or you want a simple model. If all you care about is accuracy, for example, like multicollinearity generally isn't a problem like that. So there's ways to kind of do this. And so there's a lot of techniques that you can handle. So one of the things I encourage people to do, for example, is just run it multiple times and just see how the features vary. And that kind of gives you some idea of what's going on and what are the relationships in the model. You can always, as usual, kind of use a feature association matrix and see what the relationships are between the features as well. So yeah, this is a little bit more advanced, but this is kind of what you have to do when you get in those situations and you're trying to explain what's going on there. Does that help?
Yeah, it helps. I was just thinking of basically there are sort of standard statistical ways of detecting confounding, which are based on thresholds. And so, for example, with your age of milk and age, really the factor you care about is age, and milk is just a confounded variable. And there are other ways of using statistical approaches to detect that. Whereas with other things, an increase of 0.8 to 0.9 R squared is quite significant. So you have to be careful about what you remove.
Mm-hmm.
That was the only point.
Yeah, and you know, part of this is also kind of remember to kind of level the base. So what we're trying to do here is explain what's going on in the machine learning world. Now, if you're looking for that causal explanation, right, these methodologies aren't kind of aligned to build that out. So that's one of the things we want to kind of carefully lay out, that if your goal is to kind of predict, or not to predict, but understand like what causes something else, these machine learning models will help you understand what the relationships are in the data, but they're not a substitute for that causal analysis. Okay.
Like I have like one doubt, but like what if the relation between the two independent features might be might result in a higher R square value as compared to one of them being used for prediction for the target variable. So it's like for example, if the two independent features, if they have if you just if you just compute the R score or the correlation value, if it is like almost going up to like 0.8, and for the target variable, if you select one of the features and the R square value is like 0.75, then like in those scenarios, should we consider removing the features, or should we still keep it? Because it might even have the impact on the result. Like it might add a certain noise to the result as well, which might lead to inaccurate models.
Yeah, I mean, so there's no quick answer for these kind of scenarios like that. Again, a lot of this kind of depends on kind of what you're trying to balance out here between kind of accuracy and interpretability of that. So,
okay.
No easy answer for that. So,
okay.
Yeah, the big thing I want to just make people understand is that there's tools to help kind of start to kind of ask these questions and have the conversations around this, and then figure out the best way to kind of model this that everybody agrees on. There's often not just one right way to kind of do these things. Everything usually has a bit of trade-offs like that.
Thank you.
And yeah, the permutation importance here is one way. It's for me, it's kind of a good balance of a lot of different trade-offs, but there's many other techniques you can use to also get at that kind of that feature importance as well. And there's you know, underlying issues that you can have in kind of edge cases, as Strobel's kind of pointed out with multicollinearity. There's also kind of other blog posts there, and more advanced approaches, techniques like Baruda, which are much more computationally complex, but can also give you a little bit of an edge when you're doing feature selection. Okay. All right. So I'm I don't know, I'm trying to decide how much time to spend on partial dependence, or whether to jump over to kind of explanations as well. But partial dependence is the next technique that I always encourage people to use. And the idea for partial dependence is, right, we understand, for example, that age is important or that weight is important in our machine learning model, but we want to understand how it's important. And we don't always have, if you're working with a linear model, you get nice coefficients if they're positive or negative. We don't get that with a machine learning model. So I'm going to actually just skip here. I'm going to spend a few minutes just talking about partial dependence, and then we'll kind of try to hit explanations really quickly as well. I just want to make sure people understand kind of how we get at partial dependence, because I think it's a very useful tool. So if we go back to our example with the age, with our dragons, what we can do is we can take one particular dragon. So here we have this kind of this young red dragon. And what I want to do is take the characteristics about this dragon and get a prediction for our model for a specific age. And then I'm going to manually change the age and say, for this red dragon, suppose it was 10 years old. What would I get for the prediction? Suppose if this dragon was 15 years old, what would I get for the prediction? So you can see by kind of varying this individual prediction, I can then graph that out. So I start with that with one dragon, and then what I do is I add another dragon in there. And then I kind of carefully map out, if I change the age for this, what are the predictions that I would get? This helps me calculate the partial dependence. And now I'm going to do this for lots of dragons. Now, if I just take a look at these curves here, this is often what's called individual conditional expectation curves, ICE curves. And it gives us an idea of the relationships now between age and what our predictions are. And the most common technique is we actually take these and we actually average all these lines. And now what we do is we get an understanding for this particular model. As I change age, what's the effect on our prediction? And so this can give us some insight into, for example, what happens when I change age? Does my prediction go up or down? What is the curve of that relationship, right? Because these are nonlinear models. You won't necessarily have straight lines. We'll have different types of shapes there. But this kind of gives us a really good insight into the relationships of particular variables in a model. All right. So let me give you one example of kind of where I've kind of liked using partial dependence. And this was an example with price elasticity, where we were looking at the price of sales on orange juice. And how many people, like what happens with sales with orange juice, right? If you raise the price of orange juice, if you make the price higher, will you sell more or less? And if you raise the price, right, less, right? We took economics 101, right? Well, but the reality is we'll get into a little bit more nuance. Now, what we're going to do is build a model to understand what the relationship is between kind of the price and the sales. And we're also bringing in together some other information. We'll take into account where the stores are, the dates, whether or not there's coupons, advertising, as well as, and this is where it gets tricky, we'll take into account prices for 10 other brands. Because this is what happens kind of in the real world is you might change your price, but you're actually in a competitive market for how that works. And so this is one of the kind of the machine learning models. And you can see here, when we go and try to understand, hey, what is the relationship for this particular pile of orange juice to how much we sell? It's all over the place. So what we're looking at here is the orange line here is how much we actually sold. So you can see kind of as the price increases, so as we go on kind of to the right on the x-axis, we'll see sales are still all over the place. There's not a clear relationship between this. And this is because there's a lot of other factors going into this. It's not just the price of this orange juice. It kind of is affected by lots of other factors. But if I use the partial dependence, I get a much different story. So now if I hold, and so the partial dependence again is holding everything else constant. And now you can see, for example, as the price goes, and this is at actually about $3.46 for this kind of whatever, 128 ounce orange juice, it drops. Any idea why it drops like that? And my guess is that at around $3.50, people are like, you know what? Maybe I'm going to buy something else. Like, you know, up to $3.46, but $3.50, maybe I'll just get a smaller size. Maybe I'll get a competitor. And so as it gets kind of close to that $3.50, you can see the amount that they sell is much less. But now we get that relationship that you guys were earlier saying that, you know, as my price goes up, I sell less. But it's kind of a tool like partial dependence helps you pull that out of out of your kind of machine learning model. All right. So this is kind of, for me, kind of another standard tool. Pretty much it's implemented everywhere. There's some of the classic papers that you see on partial dependence are Friedman's back in 2001. And if you're interested in those ICE plots, for example, Goldstein's paper in 2013 has them, and there's plenty of implementations for doing that as well. Okay. Any big questions, or should I keep pressing ahead?
I was just curious about when things are priced $1.99. I always found that kind of stupid, rather than $2. Do we actually see that backed up in the data where there's a drop off of that inflection?
Yeah, I mean, this was a kind of a toy example from Dominic, and I'd have to go and calculate kind of where that would be. I mean,
but in theory, you could use this technique to figure that out, right?
Yeah, yeah, in theory, yep. My guess is right there's probably hopefully some psychological research that shows that people are willing to do that, right? There's easily ways to run experiments on something like that to really get to that. All right, so the last piece I want to focus on is predictions. So we've built a model, right? Part of what the goal of our model is to do is to figure out which dragons are likely to eat us and which ones aren't, right? We get a score for them, let's say, that tells us which ones are ones to worry about, our red dragon over here versus our blue dragon over here. One of the other things that's often useful is getting explanations as well. So this is something that's kind of really been kind of hot in machine learning the last, I'd say like about the last 4 or 5 years, is explanations, where you not only get a prediction, but the model also tells you what are the features or variables that were most influential for that prediction. So for example, like why did this particular dragon get a score of 9.1? Well, in this case, the number of past kills, it must have had a lot of past kills, was an important factor in that. Maybe the color, right? While gender maybe was a contravacting factor. And these explanations are something that I've seen kind of very useful in everyday scenarios. So this is taken from kind of one of my colleagues kind of built this out for a local hospital, where what they do is they have a standard model that predicts what is the likelihood that a patient is going to be readmitted. This is a big deal for hospitals, right? When they send you home, they want you to come home. They don't want you to come back really quickly, because not only is it bad for kind of in a medical way, but it actually affects their bottom line. So as part of this model, what it also does is that you can see it gives explanations as well. Like why for this particular readmission score, what was the purpose? What were the factors that led to this particular readmission score? In this case, right, the abdominal pain. What was the secondary factor? Oh, the medical specialty was unspecified. So maybe no doctor kind of looked at that person. But these explanations play a crucial role when you're working with stake end users with your model. Because one, when you're building your model, they help them understand and build trust in the model. Is this something I really want to use? Let me test your model in 4 or 5 edge cases. Are the explanations that are coming out, is what the factors your model using, does that sync up with what my domain expert thinks, right? If she agrees with that model, well then maybe, right, there is some validity to this model. If not, maybe we need to rethink kind of how this model is and figure out why it's not working correctly. End users also like this because it gives them some context, right? When we get a score of 63.7, now they know what are the factors that led to that. And so that context really helps them make different types of decisions, because based on those factors, based on just the number, they might not know exactly what to do, but by adding in those factors, it gives them several different ways that they might be able to respond. Now, one of the traditional techniques, kind of one of the first early techniques, maybe not traditional, was LIME, kind of a local interpretable model agnostic explanations. In earlier versions of this paper, I used to go through and kind of demonstrate kind of why, kind of the number of flaws with LIME. I think at this point, everybody kind of knows those flaws. I'm happy to kind of point people to kind of earlier work that kind of does that. Essentially, if you just spend a little bit of time with LIME, you'll realize why it has a number of flaws as an explanation technique. What kind of instead is becoming kind of much more standard is what I call, what it's called Shapley values. So let me spend the last kind of few minutes on this, and let me know if there's questions as I'm going through this as well. So if people have questions, I'm happy to kind of release time and doing that, but ask them right away. Otherwise, I'll kind of keep going. Is that fair? Is that okay? So the way I like to think about kind of Shapley values is, so I live in central Illinois, right? It snows and I have a teenager. And every once in a while, he'll get his car stuck down the street, right? He'll tend to drive over the curb and we have to kind of push it in the snow and get it going. Now, right, I'll grab the teenager, I'll grab one of the other teenagers, right? Like 3 or 4 of us will go out there, kind of start pushing the car. Now, my feeling is whenever I'm kind of pushing that car, right? If you've ever kind of pushed that car, I'm heaving out of it, right? I'm pushing, I'm hard. I'm like sweating, trying to get that car going. But I always feel like, you know, some of the other kids are just standing there with their hands up. Like they're just like, I don't think my perception is they're not really pushing. They're not really contributing at all in this way, right? They show up, but they're not contributing. Well, what Shapley values allows us to do is when we have these kind of cooperative games, when we have these endeavors where it's people or features that are all working at the same way, Shapley values helps to unpack what is the actual contribution of each of these people. And so this is, it's comes out of the non-machine learning world, comes out of game theory. It's won kind of some minor prizes, things like the Nobel Prize, but kind of the intuition of this Shapley values is, for example, you know, imagine I have my car stuck here. I need 85 units of force to move it. What we want to do is understand how much each person contributes to doing this, right? So if it's me and my kid, right, we can contribute 80, but hey, if the rock comes by, at this point, right, all he needs to do is contribute 10, right? I know he's much stronger than me, but if he just contributes 10, that's enough to kind of get the car moving along with that, right? And if we look at a different scenario, maybe in that scenario where Rock got his car stuck, or Rock got my car stuck, right? He's going to be heaving a lot more to get this car unstuck, right? But I could just come along, and then as long as the Rock's pushing, I can just kind of one finger it, get that car moving along with that. And so the idea of the Shapley values is can we start understanding what these contributions are to us? And so I'm running low on time, so I just want to kind of give you, I want to give people just the essence of it here. I have much detailed slides that go through the calculations of this, but what I want to leave you with is that kind of the fancy formula for Shapley values is essentially looking at kind of all these different scenarios where my car can get stuck. Can I figure out what the marginal contribution is of everyone? And if I can kind of take the average of that, that allows me to understand how much on average do I really kind of push when I push the car in these different scenarios. And the cool thing is we can take this to machine learning. And what we can do is for an individual prediction, I can understand compared to a baseline or average prediction, what are the features for a particular prediction? So this is the level of a prediction. All the earlier stuff we were talking about is at the level of a model, but for a particular prediction, what are the variables that are actually affecting this prediction? And so this gives us is able to tell us, just like I wanted to in that hospital readmissions, like what are the factors that are causing it? Now I can see, for example, right, this is Boston housing, right? Like, right, the LSTAT factor is the most important feature for the most important component for this prediction. All right, let me take a second, make sure kind of people have this. I have other examples of this as well. But this is the cool thing about the Shapley values is we can actually start understanding for a given prediction how different features are contributing to it. It has some nice properties, like if you use a standard kind of regression problem, you can even get everything can kind of nicely sum up between the base value and your prediction as well. So it provides a very nice way to help us understand what's going on. All right, I'm going to keep going here. I got just like one more point. Now, the one thing I'd like to point out about Shapley values is there's a ton of ways to do it. So I gave you the kind of the example, right, of pushing the cars. But the reality is when we get to machine learning, where we have lots and lots of different features and combinations. So with 3 people, it's a pretty simple combination. You can think about it, right? If I had 100 people pushing my car, like trying to figure out all the different combinations of those people for pushing my car, the mathematics of that gets very tough. So there's lots of these are essentially approximations to get to our Shapley values, because only in kind of some small scenarios, we can actually get to the trap values. So what I want to do though is, for the last 2 minutes, is for folks that are comfortable with Shapley values, I'm going to skip how to calculate that stuff, is I want to point out that there's some cool things you can do with Shapley values. Once you get the Shapley values, you can generate something similar to that feature impact where I had before. We can sum up all the individual predictions and see, hey, what are the features that are the most important across every prediction? You can use Shapley values to start diving into interactions, right? So for example, I know when we talked here about features that are correlated and interacting with each other. Now we can use tools like Shapley value to see, for example, what's the effect of, what's the interactions between age and gender in this case. So you can see here, for example, like males have a much lower, right? They're more likely to die in this scenario, while women are much better. But the only way we can figure this out is by actually considering that interaction between age and gender. Otherwise, if we looked at it on average, that would be neutralized out. Other cool techniques you can use is, you can use Shapley for feature selection. I often recommend using permutation, but there's no reason why you can't use it to figure out, once you start with 100 features, as you're trying to kind of narrow down the set of features, you can use the Shapley values to do that. And then finally, there's some techniques that we can go into. I probably won't have a chance to go into them here. Let me just mention them. Kind of what I call explanation clustering. I'll just leave it on the explanation clustering slide, where we can actually take all these explanations that come out of using a technique, all the explanations that come out, we can actually apply clustering methodologies to them. And that helps us understand kind of what are the different groups in our data. And it's something called like a supervised clustering. And this is a relatively new approach. In Scott's shop paper, he mentions it all as well. And we built out a bunch of resources on this technique that's available as well. So this is kind of some of the cool advanced stuff you can do with the Shapley values. Okay. I see I'm almost at time, and of course, I didn't see many other questions, but I should leave a few minutes here for questions. I threw a lot at you at the end there.
Rajiv, one thing, would it be possible for you to share the presentation? Because I think it is really something, we have a lot of good content here. So probably if we want to share it with students, would that be possible?
Yes. So actually, if you go to this bit.ly site, it's my GitHub. I actually have a copy. I email me and bug me and I'll refresh it with the latest version of the slide. But sure. I have a kind of copy of the slide, as well as some of the notebooks for some of the examples of, for example, with the feature impact, with the age example that I showed, as well as some of the other things, like, for example, the issues with Lyme as well. There's some notebooks there.
Yeah, I think that would be great. If there are any questions, you can unmute yourself or write in the chat box.